We want to be able to find the derivative of a function in a direction that you control. And you control the direction by finding a parallel line to the given tangent line, and it's that line that's parallel, that's protruding out from the origin, that you turn, and when you turn it, it gives you a different direction, derivative in the direction of however you navigate. So we call this a directional derivative. It's going to be found at some fixed point in the direction of a unit vector, and the unit vector is the vector that will protrude from the origin. Its vector, that unit vector, will be parallel to whatever vector that you're trying to get the derivative for. So it's one thing, but we're going to parallel it to be able to calculate the derivative of that particular function in whatever direction that you point it in. It's almost like, in the sense, if you have a vehicle, that vehicle turns based on the steering wheel, but the steering wheel is not what's making the vehicle turn. There's other factors that's making the vehicle turn in terms of the wheel motion, and that type thing, and all of the mechanics that's associated with it. But you control the wheel. So what if you control the wheel, and when you turn, the vehicle turns in whatever direction that you want to put it in? And so think about the steering wheel as being this unit vector u, and think about the so-called directional derivative would be the vehicle itself. And so you navigate, but when you navigate it, the vehicle goes into different areas, thus different slopes that it takes on. So if we're looking at this region here, this mountainous region, and we call that a surface. Here's some surface, and we want to be able to, if I'm at some point on this surface, and I want to be able to find the derivative as I slope down, say for example in this direction, or you may go down a different direction. Well, obviously, going down different directions, you're going to get different derivatives. So a different velocity, if you will. As you slope down, you may slope up, it doesn't matter. And so the key here is to be able to find that so-called derivative. We want to use a very strong property in mathematics, and that is, if I talk about two parallel lines or two parallel planes, then one of those lines that are parallel I control, and when I control it, it controls the other, since they're forced to be parallel. So if I turn one, the other guy turns. Now the one that I turn is the one that I can manipulate, and I can manipulate it because I can pick some vector from the origin that's always parallel to the vector I investigate. That's the idea that we try to build with this, and then we look at the proof to be able to cook up such a formula. So we start with this surface, the space. We start with this, and we're saying that this is supposed to be a model of what's happening here. And so what we do is we want to investigate, if you take this image, this is what this guy looks like, but we're taking this in pieces. So if I look, basically I'm in the space here. This is the point P, and then this is the point Q. So I want to find the directional derivative at P in the direction of Q. So I want to find the derivative at P in this direction of Q. But here's what I do. It's hard to get this guy. What's easier is if I say, let U be parallel to PQ, right? let this vector u, a unit vector that protrudes from the origin, be parallel to PQ. This is P, and then there's a point Q over there. There it is right here. Right? So let's take a unit vector from the origin and say let that unit vector u be parallel to PQ. If I do that, then I put the strength on u because I can manipulate it. It's right there at the origin. Now, P is fixed, and you always know in mathematics a fixed point when we talk about x naught, y naught, z naught. Right? That subscript, the naught, denotes that this point is fixed. When you see x and y, that means it's arbitrary. It could be anything. Right? So what we're saying here is you fix P. Now, if Q is in that direction, I compute the directional derivative over there to my left. But if Q is this way, right, because Q is arbitrary, if Q is directly in front of me, let's say going south, so I compute now the derivative at P in the direction of Q pointing this way. But my pointing in terms of controlling PQ is actually being controlled by this unit vector U. So I'm going to turn, this is the stern wheel, I'm going to turn U. There's an angle here from U to the y-axis that we call theta. So I turn that stern wheel, or I turn that angle, and when I turn U, PQ also changes as well. Well, there's theta here from U, not to Y, but to the x-axis, and we'll put it over here. We create a perpendicular plane. So we want to be able to find a formula to calculate the directional derivative at P in the direction of Q, or tantamount to saying find the directional derivative, oh, that's theta, my slash didn't come through, find the directional derivative of the function f at P in the direction of U, because U is said to be parallel to PQ anyway. So whether I talk about PQ or if I talk about U, I'm talking about the same, because these lines are parallel. Okay, there it is. So here's the argument. I want to construct, again, a formula for the directional derivative of a function f in the direction of a unit vector u, or in the direction of a vector PQ. I use a very neat property in mathematics, because if you looked at it, our choice of u was to make the vector u parallel to PQ. That was our choice. So let u and PQ be parallel. Then we have the property from linear algebra that parallel lines differ by a scalar. Parallel lines are scalar multiples. So if that be the case, we take t to be a scalar. Let t be any scalar, and then we have the scalar t times u is equal to PQ. Let's see how that looks, and let's see if we can build the formula, and then we can work some problems. So take u to be parallel to PQ, then there exists some scalar such that t times u is equal to PQ. That is to say that t times this vector u is equal to PQ. The coordinates here would be x minus x naught, comma, y minus y naught. So P has the coordinates x naught, y naught. This is where Q has the coordinates x comma y. And U is set to be a unit vector defined as cosine theta. Remember that theta that we saw? Cosine theta I plus sine theta j. So if that be the case, then we have t times u, but u is cosine theta, comma, sine theta is equal to x minus x naught, comma, y minus y naught. Well, this implies that we have t times cosine theta is equal to x minus x naught, and t times sine theta is equal to y minus y naught. Now I can get x. X then has this relation that x is equal to x naught plus t times cosine theta, and y is equal to y naught plus t times sine theta. Again, we are investigating here. If we put the diagram back, we get some vector u, and then we get this pq. Now up in space, I want to be able to calculate the slope from P to Q. Find the slope of the secant line of the line segment PQ. You know, there's curvature there. So we're looking at it from P to Q. So why do we find the slope of the secant? Because eventually I want to find what? The slope of the tangent. Thus, that'll give me the derivative that I'm looking for. So I take the slope of the secant, then I take its limit. We get the derivative. So here, we find the slope here of the secant line. This is equal to f of x comma y minus f of x naught comma y naught all over here the numerator is the difference of the function values divided by the difference of the values that happen in the plane of xy. So in other words, downstairs, the distance from PQ and XY happens to be the distance formula for PQ. So this distance formula just gives us the square root of x minus x naught to be squared plus y minus y naught to be squared. But we said that x is equal to this. X is x naught plus t cosine theta. And y is y naught plus t sine theta. So this slope gives us f of, here x becomes x naught plus t cosine theta, comma, y naught plus t sine theta minus x naught, comma, y naught, all over. Now, if you take that square root, notice what the square root is. See if I can squeeze it here. That if I get from what's in red, these two boxes, if I solve for x minus x naught to be squared, let's see, x minus x naught, would you agree that that's t times cosine theta? Yes, sir. So if I square that, you get t squared cosine squared theta. Over here, y minus y naught, you agree that that's t times sine theta, right? So when I square, I get t squared cosine squared theta. So if I plug that information downstairs, then we have the square root of t squared cosine squared theta plus t squared sine squared theta. The distance from P to Q in the XY plane. It's good old-fashioned distance formula. So downstairs, when I factor out the t squared, I get cosine squared plus sine squared, so that gives me 1. That's the square root of t squared. So downstairs, I get the absolute value of t. So the slope of the secant line is f of x naught plus t cosine theta, comma, y naught plus t sine theta minus f of x naught, y naught, all over the absolute value of t. Now, this slope yields the tangent by sending t to 0. So thus we have this slope of the tangent line is the limit as t goes to 0 of f of x naught plus t cosine theta minus y naught plus t sine theta minus f of x naught y naught all over t. Now, it is only in that you understand now that this limit is a formula for the directional derivative. What is that? That's it. Yes, sir. You let t cover positive numbers. Let t cover positive real numbers. Now, why is that the case? T becomes a function of time. That's what it is. So, the theorem, of which I don't have time and space to prove here, the theorem takes the definition and says, notice, you know, in my form, we had the limit of f of t naught, and it was y naught, but then over here was x naught and y naught as well, right? So if you change that and investigate that at x and y, then this becomes x plus t cosine theta, y plus t sine theta, minus f of x comma y. So whatever x is here has to be the same x over here, right? And whatever y is there, the same thing. The theorem says that the formula that you want is this. Now, I'm going to manipulate this to make sure you understand, because sometimes when we calculate the directional derivative, you may not see directly cosine theta. You may not see directly sine theta. Take my glasses off. I got to get close so I can see it, right? Okay. Yeah. So the formula that we use, and it is obvious that this formula comes and it is a direct implication of the definition. So we use the formula. Okay. Now, as we go along, I'll show you how we control it so that you understand it. Let's look at the first problem. Find the directional derivative of the function f at p in the direction of the unit vector u equals to cosine theta I plus sine theta j. So the first thing we better do is to make sure that we have the right unit vector. This is cosine of negative power over 6 I plus sine of negative power over 6 j. Now I need some help. So if I look at the 30, 60, 90, break this up like I showed you before. And over here is 60 degrees. This is the 30 degrees of power over 6. So the cosine of power over 6 is square root of 3 over 2. And the sine of power over 6 is 1/2. Here it says negative, so that means that this negative power over 6 is in the fourth quadrant. So if I'm here, that means that this becomes 2 pi minus the reference angle. we already got the angle. So here, all I need is the sign, right? What's the sign for x or cosine? It's going to be positive, and then what's the sign for y? It's going to be negative here in this quadrant. So here the u comes out to be pi over the square root of 3 over 2, because cosine is positive over here, times I. But the sign here, the y, would be negative. So this is minus 1/2 j. So the cosine theta is the square root of 3 over 2, and the sine theta is negative 1/2. So we'll use that for that formula. The formula also called for those partial derivatives. So we need the partial of f with respect to x. So if you will, f is equal to y times x plus y to the negative first power. So this is negative y times x plus y to the negative second power, or negative y over x plus y to the second. We have to find, here's how, well, let me write the next one. The partial of f with respect to y. With this one, we use the quotient rule because I have a y upstairs and downstairs. So it's the derivative of the numerator. And I don't know, I've been grading so many papers with different classes, but I noticed that somebody had the quotient rule backwards, and you know, I'm grading calculus 1, 2, and 3 all at the same time, so I forget what class they came from. But yeah, you don't want to make that mistake. Right? So the quotient rule, the derivative of the numerator, which is 1, times our denominator. Well, sorry, my statement is ambiguous. You don't want to make that mistake, meaning you don't want to mix up the quotient rule. My statement, I was kind of out there. It also could imply you don't want to grade calculus 1, calculus 2, calculus 3 at the same time too, right? Yeah. So the derivative of the numerator times our denominator minus our numerator times the derivative of our denominator, which is just 1, all over our denominator squared. So this is just x over x plus y to the second. Now here's how this function looks. This is the directional derivative. It's the directional derivative in the direction of u of the function f, evaluated always at p. So evaluated at 3, 0. This is equal to the partial derivative of f at x at the point 3, 0 times the cosine theta, then plus the partial derivative of f with respect to y at the point, always at the point p, because that's the point that's fixed. It's when I change u, right, when I change the vector u, that I get a different directional derivative. Here, this is times sine theta. So now, if we evaluate here, x is equal to 3, y is equal to 0. So if y is equal to 0 and x is equal to 3, then the partial of f with respect to x at 3, 0 is 0. Here the partial of f with respect to y at 3, 0, where x is 3, so I get 3 over, this is 3 plus 0 to be squared, so I get 1/3. So this directional derivative in the direction of u at the point, at f evaluated at the point 3, 0 is equal to the first partial derivative, which is 0, times the cosine square root of 3 over 2, then plus the partial derivative of f with respect to y, that was 1/3, times sine theta, and sine theta is the negative 1/2. So here we get negative 1 over 6. So wherever they are here at this function at the point 3 comma 0, and as they move in the direction of theta, here they're traveling downward because our directional derivative is negative. Is that okay? Let me give you that one to do. See if you can get that one. Yes. Yeah. Negative 2 over the square root of 2, or just negative square root of 2. Yep. That's good. Everybody happy with that? Good. That one is easier. That previous one that I worked was a fraction, so I had to use the quotient rule. This, you just take the derivatives, you get 2x and 2y, right? And then cosine theta is the square root of 2 over 2, sine theta is the square root of 2 over 2. So you plug in the information, you should get it very quickly. The directional derivative of the function in the direction of u at the point 1 comma negative 2. This is 2 times x times cosine power over 4 plus 2y times sine of power over 4. Well, this is 2 times 1 times square root of 2 over 2 plus 2 times negative 2 times square root of 2 over 2. So here, get square root of 2 minus 2 times the square root of 2. Let's get negative square root of 2. Everybody happy with that? Yes, sir. The directional derivative is no longer right. It's a scalar, right? The directional derivative is a scalar. See that? For the directional derivative, there's no I and j anymore. Good question. All right. Now here, find the directional derivative of the function at p in the direction of the vector v. Well, here v is not a unit vector, so that's a little bit different. So what we do, because the definition for the directional derivative is based on a unit vector. Right? How do you know if a vector is a unit vector or not? You take its norm. And if the norm of that vector is 1, then it's a unit vector. If its norm is not 1, then you can make it a unit vector. By taking that vector divided by its norm, that becomes a unit vector, right? So here, let's take the norm of v. That gives us the square root of 9 plus 16 gives us 5. We don't get 1. Oops. So here's what we do is we say let u equal to v divided by the norm of v. That becomes a unit vector. So this is 3 over 5i minus 4 over 5j. So now that then becomes our unit vector u that we need for the formula. So to see it, the cosine theta is 3 over 5, and the sine theta is negative 4 over 5. So now we need the partial derivatives. The partial of g with respect to x is 1/2 times x squared plus y squared to the negative 1/2 times 2x, which that just becomes, x over the square root. You remember that? And since x and y are symmetric, the partial of g with respect to y has the same form. This is y all over the square root of x squared plus y squared. Brother Donnie, are you with me? Okay, good. So now we find the partials at the point P, always at P. So this is 3 all over the square root of 9 plus 16. So that's just 3 over 5. And the partial of g with respect to y at the point 3, 4 is 4 over 5. So now we find its directional derivative, the derivative, of f, well, this is g, in the direction here of u at the point 3, 4. So that becomes the partial with respect to x, that's 3 over 5, times the cosine, and we got the cosine to be 3 over 5. Then plus the partial of g with respect to y, that's 4 over 5, times sine theta, and that was negative 4 over 5. So we get 9 minus 16 over 25. That's just negative 7 over 25. Kind of get the idea with these last few that we've done. When the directional derivative comes out to be negative, that they're up top and they're sloping down. Is that okay? See how you handle this one. How do you deal with that v over there, that vector v, right? Find the directional derivative of the function at p in the direction of the vector v. The question is, first you have to investigate, is v a unit vector? If it is, then v becomes u. If it's not, then you have to write u as v divided by the norm of v. So how do you figure out if a vector is a unit vector? What do? You take the norm, right? Or the magnitude, if you will. Yes. And when you find the magnitude of v, what do you get? You get 1. Very good. You should get 1 for that problem. So v is a unit vector, so just let u equal to v. Now be careful with the partial derivatives. Get those x's and y's kind of splashed through there. As Angel Eyes told his merry men and the good, the bad, the ugly. He said there's a couple of them. He said, so watch out. There was a few of those X's and Y's, so watch out. Oh, my little son Zion, he wanted me to tell you all, take it easy, man. So, I don't know if y'all into this, is it Fortnite? The game Fortnite, and there's some guy on YouTube, he plays Fortnite like 23 hours a day. And that's one of his phrases. He says, take it easy, man. That's what I heard. Yeah.
It's like we go through all this stuff, go to college and everything, and then we make like a tenth of what some kid makes playing video games.
Isn't that crazy?
I know,
Yeah, go figure. Yeah, the movie's coming out, Professional Tag. When is that movie supposed to be coming out? Yeah. Yeah. About Tic Tag. It's some guys that when they were kids they played like tic tag, you know, but then now they're grown ups, they're adults, and they still play it, and they live all across the country, but they make it their best to kind of find one of their best friends and tag them and run off, and we saw the commercial trailer for the movie, and they were at the wedding, and they were still doing. The guy was getting married, and they were still doing the tic tag. Yeah. So I don't know when it's coming out, but is it out? No, wait till I tell my wife that. Man, we're gonna go see it. I gotta take her out to see that. We'll probably go after church. Okay. Did you get 7? Did you get 7 for that one? You got 1? Maybe I got it wrong. So cosine theta is 3 over 5, and sine theta 4 over 5. Find the partial of f with respect to x. I got 3 minus 4y. I evaluate this guy at the point 1, 2, so I get 3 minus 8. negative 5. Okay. Then the partial of f with respect to y, get negative 4x plus 9. Evaluate this at the point 1 comma 2. So it gives me negative 4 plus 9. So that gives me 5. So we find the directional derivative of the function in the direction here of u, and since this guy is a unit vector, that becomes u. So this is negative 5 times 3 over 5 plus 5 times 4 over 5. And yes, you get 1. Yeah, I was moving too fast. Good, good. So you got 1. Wonderful. Any questions? Now, each problem that I'm doing a problem here for the directional derivative, but they change it a little bit. They're changing the vector that you want to find the directional derivative in that direction for. They change it. Like first, the problem, they gave you the unit vector, right? Then the next problem, they gave you a vector v, which may or may not be a unit vector. But now, what if they just give you the line segment PQ? Hmm? We use the idea that we know that U is parallel to PQ, right? So we're still basically talking about the same thing. So here, the line segment PQ is 4 minus 1, we get 3, and then 5 minus 1, we get 4. So let V equal to PQ. The unit vector, U, we set that to be V divided by the norm of V. So I find the norm of V, it's the same thing as saying the norm of PQ. So that's the square root of 3 squared plus 4 squared. So we get 5. So U becomes 3 over 5 comma 4 over 5. And you get the idea when you work these problems, you kind of think that Larson just likes these numbers 3, 4, and 5. I do too. They're smooth, right? So now the partial of f with respect to x is 2x. Then this partial at the point 1 comma 1, always at the point P, always at P, in the direction of Q. So this is 2 partial of f with respect to y, 6y. Here, this partial evaluated at the point 1 comma 1 is 6. So we put them all together and shake it around, and that's what it's all about. So, hokey pokey. No. So the directional derivative of f in the direction here, we found our u at the point 1 comma 1. Again, this is the partial of f with respect to x times a cosine plus the partial of f with respect to y times sine theta. We found the partial to equal to 2. The cosine is 3 over 5 plus the partial of f with respect to y is 6 times the sine, that's 4 over 5. So we get 6 plus 24 over 5 You get 30 divided by 5, just 6. Okay. Yes, sir. Gotcha. Okay. We're good. Okay. Good deal. Those partial derivatives, when you collect them and you talk about them as a unit, that is, if I find the partial of f with respect to x, the partial of f with respect to y, and I make that a vector, that's called the gradient. So just take all the partial derivatives and make them a point, then that's called the gradient. So here, f is some function of x and y, and z could be a function of several variables. Here we just talk about a function of 2 variables. You can expand that to 3 variables and so on. So here we call the so-called gradient, if the partials exist, the gradient of f at the point x comma y, just the partial of f with respect to x, I, plus the partial of f with respect to y. So we've been finding these already, so we're just collecting them and just giving them a neat name now. Does anybody see that? It's a Western called The White Buffalo. It's an old movie, maybe in the 70s. Charles Bronson was in it. And then, I forget the Indian chief. He was a real Indian chief. And he played the role of, I think, Sitting Bull. I think he played Sitting Bull or he played Geronimo. But they both met each other. And according to the legend, they had been at odds before, somewhere up in the, I don't know if in the Dakota somewhere. They were at odds with something. I don't know if it was even back when Wild Bill was a Union scout. But when they met this time, this was years later, and Buffalo Bill, Wild Bill, I'm sorry, said that his name was not Wild Bill. He said some other name. And Chief, I don't know if he was playing Geronimo or Sitting Bull, he said his name wasn't Sitting Bull. He said, they called me Running Worm or something like that, you know. It was pretty cool. And Wild Bill gave a fake name too, so, you know. And but they're after this, they're hunting this white buffalo. And this white buffalo is supposed to be like this mean, big, I mean, you dream nightmares about this white buffalo. And apparently both they had nightmares about it. And I want to say that this buffalo came through and stomped out some kids in some like Indian little camp. And I think it killed Sitting Bull's child or grandchild or something. So he had it out for this buffalo. And Wild Bill had these bad dreams, and he had bad dreams for real, always thinking that somebody was going to kill him, and so that kind of was personified in this white buffalo. So he wanted to kill this buffalo, and the Indian chief wanted to kill the buffalo. So when they said, when we kill this buffalo, we're going to part ways. I said, okay. So the whole movie is about them kind of hanging out together, trying to kill this buffalo. So when they finally kill the buffalo, they're like divided by a valley, and so Wild Bill said, "What is your name?" And he said, "I know it's not Running Worm." Yeah, no. and Wild Bill, he said, I'm Bill Hickok, whatever. And so the Indian said, he said his name in his Indian dialect, and then he said, but they call me Sitting Bull or something like that, you know. And then he raised his horse up and he rode off in the dusty yonder, you know. It's a really good movie, man. But anyway, I thought about that because here, these two guys, they were under some fake alias, but then when everything smoke got cleared, they said, hey, this is my real name. So So my point is, we've been dealing with the gradient all along. We just didn't call it the gradient. So now that we've killed the white buffalo, this is the gradient. Sir? Man, we got to move on, man. Oh man. Now, in terms of how this gradient, uh, how it looks, um, the gradient is actually a a normal vector, and I think from this graph you really can't see, and I think we'll bump into it eventually as we go along, and I think I have a better depiction of it as we move on through here. There's an alternative form for the directional derivative. The directional derivative, if you notice how the formula was given, this guy said this, that it's the partial of f with respect to x times cosine theta plus the partial of f with respect to y times sine theta. But if you take the gradient of f, at some point x comma y, and use the dot product of it with that unit vector, you get exactly the formula that we had before. So that's all that we're doing here with this. Just an alternative form. You can use that. Doesn't matter. So first, let's find the gradient. Then I have a question where we ask find the directional derivative by using the gradient. So here we just want to find the gradient of z. We need its partials, the partial of z with respect to x. If it's the natural log, that's interesting. Well, be. I read that wrong. I read that earlier as the natural log of everything, but it's just the natural log of the numerator. So just means it's more work. So we take the derivative of z with respect to x. That top guy, the derivative of the natural log is 1 over the term times the derivative of x squared minus y with respect to x. That's 2x. So this is a quotient, so this becomes the derivative of the numerator times our denominator times x, and then minus our numerator, the natural log of x squared minus y, times the derivative of our denominator, which is just 1, and this is all over our denominator squared. Take that derivative of that negative 4, that's just 0, so that goes out. So here we have 2x squared over x squared minus y minus the natural log of x squared minus y. That's all over x squared. We compute that at the point 2 comma 3. So we get 4 times 2, that's the 8, divided by 4 minus 3, that's 1, minus the natural log of 4 minus 3, that's 1, and that's all over 2 squared, so that's 4. What's the natural log of 1? 0. So this is just 8 divided by 4, or just 2. Now you got to find that partial of z with respect to y. Right. It's a little bit better. There, since it's just the derivative with respect to y, we don't use the quotient rule. X here is just a coefficient. So, but since y is within the natural log, I still have to deal with that. So this is 1 over x squared minus y times the derivative of x squared minus y with respect to y. That's just negative 1. and then it's just divided by its coefficient of x. The derivative of that negative 4 is just 0. So this is negative x all over x squared minus y. We compute this guy at the point 2 comma 3. So this is negative 2 all over 4 minus 3. That's just negative 2. So the gradient of z at the point 2 comma 3 is 2 comma negative 2. You can write it like that, or you can say 2I minus 2j. All right. Now, for some reason, the problem that I'm working is always a little bit harder than the one that I give you. So you do this one. Shouldn't take you no time with that. This was like, in that little subsection, this was like the first problem, and then the next problem is the problem that I'm doing. So I do the hard one, you do the easy one. Let's take a 5-minute break too. So it's 9:29. Let's come back at 9:35. You get 3I plus 10J? Yep, good. What's that? You said there's no. Yeah, for this problem, yeah, x is 2 and y is 1. It's just 3, right? Okay, that's what you mean, just leave it alone. Right. It becomes a, you don't do that. Mr. Downey, take a break, please. I don't want to pause this recording because I've done that before and it's canceled out everything. So this technology, man, is not good sometimes.
There'll be a scroll bar on the video.
Hmm.
There'll be a scroll bar on the video.
That's right. Exactly. I'm going to finish this section today. My plan was to do 13.6 and 13.7 today. I'm going to finish this section, then we'll be done for today. On Monday, I will cover 13.7 and 13.8, and then on Tuesday, that would leave just one section. I skipped 13.9. I'll cover on Tuesday 13.10, and then we'll look at a review for the exam. And that exam would be next Thursday. Okay? Yes, I do. Yes, sir. Yep. So now use the gradient to find the directional derivative at P in the direction of V, and we want to make sure that V is indeed a unit vector. So I'm going to take the norm of V, and that is the square root of 3 over 3 to be squared plus negative square root of 3 over 3 to be squared plus the square root of 3 over 3 to be squared. So here we get 3 over 9 plus 3 over 9 plus 3 over 9. That gives us 1. So now the partial derivatives, I'm going to go ahead and compute them at the value, since those partials are easy to get. That's just 2 times x, so you just get 2 times 1. Partial of f with respect to y at the point 1 comma 1 comma 1 is 2 times y, or just 2 times 1, just 2. Then the partial of f with respect to z at the point 1 comma 1 comma 1 is 2 times z. It's 2 times 1. Just get 2. So this directional derivative in the direction of v, since v is a unit vector of the function evaluated at the point p 1 comma 1 comma 1, they say here to use the gradient of f evaluated at the point times the unit vector, and it's actually v here that we're using. So that becomes 2 comma 2 comma 2 dot product with the square root of 3 over 3 comma negative the square root of 3 over 3 comma the square root of 3 over 3. So we find this directional derivative, and that's just 2 times the square root of 3 over 3 minus 2 times the square root of 3 over 3 plus 2 times the square root of 3 over 3. Just get 2 times the square root of 3 over 3. Is that okay? Yes, sir. The gradient is partial derivatives. Again, before those partial derivatives, that was an illustration of the running worm, but it was the same thing as the gradient. So we've been doing the gradient anyway, we just wouldn't call it the gradient, right? Yeah. Joshua, you have to go and watch The White Buffalo. Yeah, it's cool stuff. All righty. All righty, you try. So, on that one, you're given PQ, so you let PQ equal to V, then you test to see if it's a unit vector. I don't believe it is. So then you have to find that unit vector based on V. Negative 20 over the square root of 5, or negative 4 times the square root of 5. What'd you get? Yeah. Hmm. You got something, Joshua? Still working? What you got? You have 20 over the square root of what? Huh. Yeah, we're all getting three different values. So, what'd you get, India? And what'd you get, John?
After identified, I think it was 2 squared 5, but negative 40 squared.
Huh. Isn't that what you got? Oh, no.
Yeah. What do you get for that? 42?
I didn't even find mine like that. I found mine the old way. I didn't even use the gradient. I got negative 6 and negative 8. But I could be wrong. Let's go through it and see what's happening. I'm getting nervous. So 3 minus the negative 1 is 3 plus 1, that's 4. And then 6 minus 4 is 2. This norm, you call it V if you want. Just the norm of that, 16 plus 4, get the square root of 20, or 2 times the square root of 5. The partial of f with respect to x is 6x. We find this at the point negative 1 comma 4. We get negative 6. Partial of f with respect to y is negative 2y. We find this partial at the point negative 1 comma 4. Get negative 8. Is everybody happy so far? It's always at the point P. Yeah, the directional derivative is always evaluated at the point P because P is fixed. It's always at that point. So the unit vector U is, and I just kept it as PQ divided by the norm of PQ. You could call it V, and V divided by the norm of V, that's fine too. So this is 4 over, well, 4 over 2 times the square root of 5, comma, 2 all over 2 square root of 5. Okay. So this is 2 over the square root of 5, and this is 1 over the square root of 5. No, P is 1 comma 1. So this is a different problem, right?
Yes, sir. It's a different problem, but I use that for.
But that's PQ. That's not P.
I know it.
Right.
Yeah, but that's what I know that, but I'm just saying that's why I done that because I saw it right here 3/5, 4/5.
Yeah, that's for the unit vector, but you have the partial derivatives. So these are the guys that you found at the point P, 1 comma 1, 2 and 6. So that's 2 there times 3 over 5, and then plus the 6 here times the 4 over 5.
Okay.
But here you're evaluating the partial derivatives there and also here at the point P.
Okay.
Yes, sir.
Yeah, I appreciate it.
Okay, yep. So this is the gradient of f at the point negative 1, 4, dot product with u, and that gradient is negative 6 comma negative 8. Then u is 2 over the square root of 5 comma 1 over the square root of 5. So we get negative 12 over the square root of 5 minus 8 over the square root of 5, negative 20 over the square root of 5, or just negative 4 times the square root of 5. Is that okay now? Okay. Well, at least one of them I got it right. Yes, sir.
I know, so it's the same thing, but is it gonna be like, while like we did like 3i and 10j, like we found so it's the same thing, so is the gradient in like forms of like j and I? Is that the only difference? Or is
No,
it different?
no, it's the same thing. We just didn't call it the gradient, but that's all. If you take the partial derivatives and make it a point, that's the gradient.
Okay.
Okay. So if I take the partial of f with respect to x times I, then plus the partial of f with respect to y times j, that's the gradient. If I take the partial derivatives by themselves, it's not the gradient, right? But if I put the partial derivatives in the vector form, it becomes the gradient. Yeah. Now the reason why that is because that gradient is actually, in my earlier illustration, the graph didn't depict it. I think the next one I'm going to try to draw it if I don't see it. The gradient is actually the normal vector. It's perpendicular to that tangent. Let's see if I have it here. Yeah, still don't have it there. Um, if we have some surface in the XYZ space, and if I take a point here, look at the curvature about it, and from that point, if I can estimate the so-called tangent, see if I draw that with the blue. Let's say that's the tangent. That gradient, some function f, that gradient is doing this. It's always perpendicular to the tangent plane. That's what the gradient is doing. We can take a very neat property for the gradient and talk about the so-called maximum increase or minimum increase, if you will. So here, the direction of the maximum increase of f is given by the gradient, and its maximum value of the directional derivative is simply the norm of the gradient. And number 3 follows. I had a caption. See if I can scroll down to it. That talks about exactly what this is. To visualize the properties of the gradient, imagine a skier coming down a mountainside. If f of xy denotes the altitude of the skier, then the negative gradient indicates the compass direction the skier should take to ski in the path of the steepest descent. He wants to get down there really fast, right? So that maximum increase would be here, the so-called gradient of that particular function value. Another illustration of the gradient, consider the so-called temperature function, capital T. At any point in some flat metal plate, in this case, the gradient of the temperature gives the direction of the greatest temperature increase at the point. And there was the graphic for that, but I didn't pull it up from the book. But I think you get the point. So use the gradient to find the maximum value of the directional derivative at the given point. Now again, the maximum value of the directional derivative is the norm of the gradient. The maximum increase of a function is said to be the gradient itself. And then if you negate the gradient, that's said to be the maximum decrease. So here, if we want to find the maximum value of the directional derivative, you find the gradient, And then after that, take his magnitude, and that's what they're looking for. Let's see if you can get that one. Hey folks, I better rush on. I forgot I only have 5 minutes, so let me see if I can go ahead and cover this real quick. I got 2 more problems to work as well. So we're going to find f sub x. That becomes negative the square root of y. Find that at the point 0, 3. So that's just negative the square root of 3. Find f sub y. That's 2y minus x times 1/2 times y to the negative 1/2. That's 2y minus x over 2 times the square root of y. We find this partial derivative at the point 0, 3. So that's just 2 times 3. It's minus 0 divided by 2 times the square root of 3. So this is just 6. So the gradient of f at the point 0, 3 is negative square root of 3, 6. And then this maximum value is the norm of the gradient. This is the square root of the negative square root of 3 to be squared plus 6 to be squared. So you get 36 plus 3, the square root of 39. So the maximum value of the directional derivative is simply the norm of the gradient. There's another neat property of the gradient, and we call it, if you can calculate it based on a surface, it's said to be the level curve. So if f is differentiable at a point and the gradient is not equal to 0, then the gradient is normal to the level curve. Simply saying that the gradient is perpendicular to the level curve. What's the level curve? It's the tangent. So here, you find the gradient, need the partial derivatives. This is negative 2, and then this is negative 3. So here, the partial of f, the gradient of f at the point 0, 0. Well, this is fixed since f is a plane itself. So here, this is negative 2, negative 3 at every point. And just one more. The partial of f with respect to x is 2x. If you find this partial at the point 3, 4, this is just 2 times 3, we get 6. Then the partial of f with respect to y is 2y. This partial evaluated at the point 3, 4 is 2 times 4, we get 8. So here, find a normal vector to the level curve. It's just the gradient itself at the point 3, 4. And that gave us 6, 8. That's it. Okay. All right. So we're through with that.